This is Chemistry 302, Lecture 13 on the titration experiment, and in particular on using chemical equilibria ideas to help us to model the titration experiment. So we have to start off, first of all, by asking what exactly a titration is. A titration is a kind of scientific measurement that allows us to determine an unknown amount of material. So here's a beaker, for example, or an Erlenmeyer flask, and sitting in it is some water. And sitting in this water, I happen to have an unknown amount of these orange dots here. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them. The thing is, I don't know how many of them there are because they're dissolved in solution, and they've allowed the solution to achieve a certain concentration. I know for a fact that there is a certain number of moles of those orange dots. I just don't know what it is. Titration experiments let me know that answer. Let me know that it's 8. You notice this is an incredibly general sort of concept, and although I'm going to be showing it to you today for acid-base examples, the reality is that any time you're dealing with unknown concentrations of any kind of material, whether it's an acid-base chemistry experiment you're doing or even something that you're doing in biology or in physics, that ability to very carefully monitor the counting of the numbers of unknowns is a titration-like experiment. Now, in this particular case, we're going to be doing acid-base titrations. And we're going to assume right now that those orange dots there represent either an acid or a base. Let's just decide that we're going to let them represent an acid. So I'm going to write that acid down right there. Now, if I want to know that I've got acids in there, there are a variety of ways to indicate this. Here's one rather unfortunate way. I can stick my hand down in there and let it get chewed off. And then you know what I would know? I would know that there is an indication that there is acid there. Imagine, though, I started adding something to those protons. Suppose I started adding hydroxides to those protons. If I added just the right number of hydroxides to those protons, I would produce an amount of water. And I did that at the point where the number of moles of the orange dot was equal to the number of moles of the things that titrated it. In this particular case, the moles of protons, when they were titrated with an exact number of moles of hydroxide, would produce a water solution. There's a huge difference between a proton solution, the one that chews my hand off, and a water solution, one that's neutral pH. And one of the indications, obviously, is that if I stick my hand into this solution, it's chewed off. If I stick my hand into this solution, it is not. But people don't use their hands to indicate these sorts of things. They find other strategies for doing it. In particular, you're all familiar with the idea of using chemical indicators, and we'll learn about that in a minute. But understand what this titration experiment is built on. It's built on the idea that I can write down a chemical reaction in which I have some simple stoichiometry involved, in which the moles of the acid here, when they're equal to the moles of the base, produce a very different chemical system, and that I can tell the difference between that proton system and that water system, because they are very different pHs, and that will be the indication of exactly how much of those protons I had to start with. If I had 8 protons in solution, it would only take 8 hydroxides to produce the water. If I had 100 protons, it would take 100 hydroxides to be equal to that. And so if we know the amount of hydroxides I add to solution, then I can relate it to the amount of protons. And that's how we do the titration.